The recording now. Cool. Recording is started. Mic is on. Nice. Okay. So, hello again. I guess today we're going to do a three-dimensional model because I think it might come in handy later on as you're looking at doing your project and stuff. So, last I heard, Dr. Bass will probably be back next week, but if I hear anything different, I guess, well, he'll let you know. But yeah, cool. Okay. So let me open up the file that we worked on last time, and then I'll just add a case to it. So today, what my thought is I was like, we could do another cylinder, but might be kind of boring to do just another cylinder. So I thought that maybe we could look at simulating like a transfer truck type thing, since we all have experience with that and like seeing those down the interstate. So specifically, we're just going to do just the box, just the trailer, just simplify things and make it a little easier so we can still focus on just like the mechanics of Ansys, that kind of thing. But yeah, so we'll do that and go ahead and fire up Workbench if you're following along, and we'll go from there. All right. So to start, go ahead and grab another Fluid Flow Fluent project, and you can drag it here or here, wherever. No, that'll put it where you want to put it. I'm going to call this in class test 2. So since we're doing a three-dimensional simulation, last time we set this to 2D, but today you keep it as 3D. And I think that was all besides noting the directory name here, so you can find videos and files that you want to see later on. And then I think you can go ahead and right-click on geometry. So for three-dimensional modeling, there's this package called Discovery, but we're not going to use that. We're going to go ahead and do Design Modeler still. Namely because I'm much more familiar with Design Modeler. So I figured I would do that. But it actually is, I think, nice. It's a bit more like just simplistic to work with. But if you're doing like very complicated geometry, then Discovery is more like SolidWorks or Inventor. So it's a little bit more powerful. I'll launch it just to show you, but then I'm going to do Design Modeler.
Is Discovery a newer feature? Is that why?
It is. Yep. Yeah. So I think Design Modeler is like probably 2 or 3 decades old, if I had to guess. It seems very old.
Yeah.
It's like the AutoCAD for Ansys. But I think that the design, what did I call it? Discovery? Discovery. Discovery is a newer feature. In fact, I think for 2025 R2, you can't even use Space Claim anymore, which is the one I mentioned last time. That's also a 3D modeling. They just got rid of Space Claim and now it's just Discovery.
Well, it says use space plane geometry, so.
Oh, yours does?
Yeah.
Oh, okay. Yeah, I thought that they had gotten rid of it. Mine says that because I have an older version, but I thought the new one had got rid of it. Maybe not. Yeah, maybe eventually they will, but that's just what I was told. I didn't think it was going to take this long to open.
It's faster last time.
I thought it was much faster last time, but
Does it get slower if you have multiple projects in
Mhm.
file?
It does, but usually I don't really notice a difference until you hit like like maybe 7, 8, 9, 10 blocks.
Yeah.
I used to have some like particle motion simulations that had like iterations
Yeah.
and different cases and stuff, and I had maybe like 20, blocks. And at that point, you hit save, and it just sits there, and it's like, maybe. Yeah. So what you can do is if you have like another case,
Yeah.
and you want the same geometry,
Oh.
but the setup is different, then you can, well, for one, you can click that little arrow right here, and you can duplicate it if you want to just copy it and then change a couple things.
Yeah.
Or you can create a whole new case. Yeah, so you can do this and hit duplicate. Or you can, let's say, pull another fluent block here and then drag like that. And it'll just port the geometry into that new block. Yeah, yeah. So you can have like a whole tree type thing going, and it's like sharing. You can also do parametrization where you have like a table and you can say like run it a bunch of times, but this time have this value for whatever quantity, like maybe the heat flux at a boundary, have it be 10 on this iteration, then do it again with 20 and then again with 30, and it'll like do it all with successive forms. Yeah. All right, so I'll delete that guy. There it is. Nice. So you can see it's much newer looking. So I have basically zero experience with it, which is why I'm not doing it. But you can like create geometry by I think clicking this maybe, yeah, and then sketch, and you should be able to. Yeah, draw like a rectangle, and then you can click pull, and you can actually like just make geometry, Yeah. So if you ever want to play with that, you can, like for your project, maybe you want to play with it. But I'm going to go ahead and open up. Yeah, it can't handle it. It doesn't.
I'm bad about discovery.
I know. It's offended. It's taking some personal insult.
Install -50 Ansys social code.
That's right. That's right. There it is. Oh, very nice. Design modeler. So what we're going to do is similar to last time, just in 3 dimensions. So we're going to make a huge block of air, like I said, like a fish tank full of water. And then we're going to create a second block inside. And then we're just going to cut the second block away from the inside of the first block to make a void. And that void will act like a solid almost. And the fluid will flow around the void. So, transfer trucks. I found the dimensions in feet for those dimensions. So I'm going to work in feet today. And go ahead and go to, I guess it doesn't really matter. Just go and do that axis. Z, pointing towards us. And then click XY. And then come down to sketching. And rectangle. And then go ahead and draw some arbitrary rectangle just like that. And then modify, or not modify, dimensions, general dimensions, and place a dimension on the horizontal and vertical. And then also click the upper left corner and then the middle axis. And that'll give you a dimension we can use to align it evenly, left and right, up and down. So again, click the corner, click the horizontal axis, and those are the only dimensions we need. So then come down here to the details view and change this one to 100. So we have 100 feet wide with our domain. Make V2 120. H3 make half of 100, so 50. And then V4 do half of 120, so 60. And then scroll to zoom out, and you should get that. So, and also stop me if you need to, if something goes wrong on your end, and I'll help you. So hit generate. That makes that sketch, actually creates that sketch in the software. Then go to modeling. And so what we're going to do is similar to a SolidWorks or an Inventor type thing. We're going to extrude this. So go ahead and click extrude. And this is sort of like the three-dimensional version of creating a surface from Sketch, like we did last time. Now we're creating a volume from Sketch. So click that and then open up your XY plane. You'll find Sketch 1 there. Click Sketch 1 and then apply. And that'll port Sketch 1 into your extrusion tool. Then what we want to do is, like I said, we're going to subtract these bodies from each other. So we need two distinct separate bodies when we create this geometry. So what you want to do is whenever you want to have separate bodies, you want to do add frozen. Add material will fuse them together into one part. Add frozen will connect them but keep them as separate, distinct volumes. Yeah.
I'm not seeing the extrude option on my top bar. It's starting at the thin surface. Right.
What about under create? Yeah, is it there?
It's there.
Perfect. Okay. Nice.
And what was after extrude?
Extrude and then click this plus here and select Sketch 1. And then click where it says geometry. And you should see Sketch 1 appear there.
Yep.
And then make sure it says add frozen. Yep.
Okay.
Then direction vector, leave the same. Normal, leave the same. For the extent type, nope. Sorry, for direction, put both asymmetric. So this will let us extrude in both directions by different amounts. Then for the forward direction, 1, put, let's say 150 should be good. And then for FD4, put maybe 100. And then for merge topology, put no. This is another control that's similar to add frozen. It'll make sure these volumes are separate from each other. And then when that's all done, hit generate. So you should get something that looks like that. So any questions there with that? Cool. All right, I'm gonna save it real fast. All right, so now we need to make the tractor trailer trailer. So go ahead and click XY plane again. And if you notice here, it says one part, one body. So that's this. After this next step, we should have 2 parts, 2 bodies. So if you go to XY plane again, and then click up here, this little blue star button, that's add a sketch. So now you can click sketch 2, and then select sketching. And we're going to basically repeat what we did. So you can orient it to the Z-axis down here. And then rectangle, I'm gonna zoom in a bit. Make another rectangle there. And then go ahead and dimension it exactly like we did the previous time with those four dimensions. So tractor trailers are 8.5 feet wide. Yep. And they 13.5 feet tall. And then, so this would be half of 8.5, 4.25. And this part will be 6.75, half of 13.5. All right, so it should be centered just like that. Hit generate, go to modeling. And then what we want to do is go to extrude again. And go ahead and select sketch 2, apply. Instead, add material, put add frozen. Directions normal. You can leave them both as normal. And then make it 53 feet. And then as merge topology, put no. And then generate. So now you should see our tractor trailer in there. Right. So the next we want to do is right now we have these two overlapping but distinct bodies, right? Two parts, two bodies. So what we want to do is subtract one from the other. So we want to hit create and then Boolean. And then down here, instead of the operation, we want to be subtract instead of unite. Then we have these two bodies, target body, tool body. So target is what we want to remain, and tool is what is going to do the cutting. So since we want that trailer to disappear, it's the tool body. So for target body, you have to click, if you click these extrudes, it won't work. You have to click the actual solid body down here. So click the first one, that's our target body. And for tool body, click the second one. And then where it says preserve tool body, you want no, because you want it to disappear. All right, so generate. All right, and now we have Boolean here showing it applied. And this is a void now in there. So we can go to save. And that should be it for this portion.
Are they frozen for both of those, or is the second?
I left them both frozen and also put no for the merge topology. Yeah, I think you might be able to, like, for the first one, just leave a default, and for the second one, do frozen
Yeah.
and not merging topology. But just to be safe, I went into them both that way. That way it would just like not have any risk. So go ahead and go back to your workbench. Right click mesh. And actually, hang on one second. If we go to our part, yeah, down here where it says fluid solid, change that to fluid. There we go. Fluid, yeah. It's just the name. I'm gonna name it trailer.
Is it the larger body is being fluid or the smaller one?
This is the larger. Yeah. Yeah, this is the total air box. And then I'm just calling it trailer because the void in there is the trailer. Yeah. All right. So I'm gonna save that again. And to go down here. I'm saving it a lot because earlier today I was working with Ansys and I forgot to save it. And I lost like 15, 20 minutes worth of work because I was like, I ended up closing something and was like, oh no. Okay, so go ahead and update your mesh. And let that open. Well, are there any questions while it's just sitting here loading? Maybe a point I can make is in your mesh, if you let's say have a mesh size of 1 foot, so each cell is a foot by a foot by a foot in 3 dimensions, and you say, well, I want to decrease my mesh, so let's go down to half a foot instead. Keep in mind that because half a foot is going to be half by half by half, you're actually going to have 8 times as many grid cells in that case because you're doubling it in each direction. So if you did like, let's say from a foot to a tenth of a foot, you'd actually have 1,000 as many grid cells, you know? So if you do that and then it's just sitting there like clocking basically for a long time, you'll know like, oh, okay, I set it way too high. But even though it seems like it's only a factor of 10, I guess I decided not to open my meshing software. Okay, cool. So, here we go. Go ahead and go to mesh. So you can see it's pretty choppy right now. So the default value, let's extend this a little bit. They have it in meters, which is fine. We're not going to do anything too specific, so let's keep it in meters. But it's 4.5 meters approximately. Let's drop that down to maybe 2. So like I said, that's going to be quite a few more cells because of the cubic nature of that. And then go ahead and hit generate. All right, nice. So that's still maybe a little bit more choppy than I want. Let's do 1. I think 1 might be better. Okay, yeah. Okay, there we go. That's good. Good enough. So we have this now. So I'm not going to do anything special like refinements on this. I'm just going to leave it with this pretty fine mesh. But if you wanted to go in and refine around the trailer, that could be good if you were doing an actual like scientific case. But for now, what we're going to do is go ahead and name our faces. So our faces have recognizable names in the Fluent software. So go ahead and left click and then right click, create name selection, call the inlet inlet. I'm going to call the top surface top again. I'm going to call the right surface if you're in the direction of flow, the right side I'm call right. Then the bottom, I'm going to call bottom. And this left side, I'm going to call left. Then the last surface is the outlet back here. So call that one outlet. And then you can open up the name selections if you want to view all those. Make sure they look good. Then go ahead and save it. And then right-click Mesh and click Update. And you should see translation to Fluent was successful. Then you can close that and go ahead and hit Edit on Setup. All right. So I'm going to do, again, 4 cores, double precision. But I think you can only do more than one with the academic version. So, or the research version. So hit start. Let that load in.
You click double precision.
Yeah, that'll give you more floating points in your numbers.
Yeah.
So less data loss or less accuracy loss. All right. So think we're good, maybe. Yeah. Okay. So again, you can see now we have these denoting the inlet. And then on the back hand side, we have our outlet arrows. See if I can grab this over here. Okay. Cool. So what you want to do is in general, keep it on pressure because we're gonna have a low velocity since this is just a truck moving. There's no compressibility. And set to transient. So we have time effects. Gravity, I'm not gonna worry about because we're just looking at airflow. Then under models, you can open up viscous and we can start with K omega, maybe. Same as last time. And then maybe we can try, if we have time, try K epsilon or large eddy simulation and see how it looks different. But for now, keep it on K omega SST. Then I think that should be all for the models. Under materials, we already have our air, so there's no need to look into anything else there. If you double click cell zone conditions and click your trailer, you can see it's air. Well, I say trailer, but this is the fluid domain around the trailer. So it's air. That's good. You can X out of that. Then for boundary conditions, we have our bottom, which should be wall. Our inlet should be a velocity inlet. Click edit. For the magnitude, put 32. That's roughly about 71, 72 miles an hour. So highway speed. So 32 meters per second. You can hit apply and close. Then for the interior, it's just interior, nothing changed. Left should be wall. Outlet should be a pressure outlet. And again, you can hit edit and just see that the gauge pressure is 0. That's what we want. Then for right, that should be a wall. Top is a wall. And wall trailer, that's the interior walls around our trailer void. So, with that being said, that's all our boundary conditions. So that's all set up. You can think of this, I guess, like a wind tunnel, basically. And since we're keeping these outer walls as walls, and there's some interesting things to see with that as well that we'll see when we actually do our contours and things. So with that, go ahead and
Could you also think of large body as the control volume?
do what?
Could you also visualize in your head, like, the larger body is the control volume of the system?
Yeah, probably so. Yeah. Yeah, exactly. It's like a control volume, but there's nothing outside it.
Yeah.
Yeah, exactly. Yeah, so methods, I'm gonna leave them all what they are. Controls, I'm gonna leave them all what they are. Yeah, I'm gonna leave the residuals the same. But again, if you wanted to change your residuals to make it get the error down, you could change it there. Then I think that's all I'm gonna do there. So go to initialization. And I'm just gonna go ahead and initialize everything to 0 or 1, just the standard initialization. This hybrid initialization is something that I haven't used a whole lot, but my understanding is that it makes a guess so that the simulation starts closer to the answer and then it can iterate from there. So it just takes a little bit less time than if you want to start from 0. But I'm just going to start from 0 today. So then, under calculation activities, I'm going to set the autosave to every 10th iteration and hit OK. And then I'm not going to do any solution animations today because I'm going to show you something different since we did that last time. But yeah, go ahead and save it. And we will run this calculation. Nice. Okay. All right, cool. I'm gonna do a fixed time step again. But if you wanted to let your current number be the controller for your time step, you could have it be CFL based here and set your current number. But I'm gonna do fixed. So the time step to 0.01 seconds. And I'm going to do maybe, yeah, maybe it's like 200 time steps, 2 seconds of real time. And then hit calculate. So that should be pretty quick. I think it'll take us maybe like 2 or 3 minutes for that to run through. So yeah, any questions while that's calculating? So again, interpret them. Yeah, so what you're seeing there is this is your residual here, and this is the number of iterations. So the residual, right, as it's iterating to calculate the values, in this case, like velocity, pressure, that kind of thing. As iterating, it's kind of homing in on that true value. So it'll swing too low and go, oh no, I'm too low, and go back up. And it's like trying to achieve like a steady amount. And so the residual is the error between those calculations. Yeah. So when you see it drop, it'll drop down lower it'll hit the criteria we set and say, okay, that's good enough. Or it'll say, I did 20 iterations. That's my max. Now I have to move on. Then it'll move on to the next time step, and then it'll go through its solution again. So the sawtooth motion is it iterating and then moving to the next time step and then iterating again, next time step. Yeah, so that's what it's doing. Yeah, right. It's trying to converge to the true value with as little error as possible. Yeah, I guess to give you some perspective, this will take 2-3 minutes to run, but Dr. Vassal has had some simulations in the past that took like 2 weeks on an HPC. It took 2 weeks to calculate. So you can see like if you have the physics that are sophisticated enough and you have enough grid cells, even like super powerful computers can take weeks or a month to calculate a solution. I think that simulation was like a couple of seconds of real time. So it was like hardly anything because it was just that like complex.
So I don't know if you know what option say, but for pivot announcement, is there any kind of scenario where you'd want to come up with it?
Yeah. So honestly, what I use the current number one for the most part. So for a marker. So like if you have your mesh, a little section of your mesh, and this has a certain width to it. And let's say your time step is such that your fluid your particle fluid moves from here to here in that one time step dt, then you wouldn't really like that's okay because you're only going from one to the next. But what if your time step was bigger and so you move over here? So the simulation basically skipped this whole block if your time step is too large. So what the current number says is it's a ratio, and it's basically a ratio of the distance your fluid particle travels divided by the dx you have your cell there. And so if this is greater than 1, then it'll be like that's no good. And so what it'll do is it'll actually decrease this by decreasing the time until you get a value that's less than 1 or whatever you set it to. And that'll keep your time step from skipping all these cells, basically. So for example, if I went to adaptive and I set my current number to 0.8, then anytime it calculates the current number and gets greater than 1, it'll decrease the time step until it gets a value that is 0.8 or less. And then it'll step forward with that time step. And if it again goes, oh no, I have a current number more than 1 or more than 0.8, I'll decrease my time step again until I have a lesser. So it'll keep you in your a good bound that way. Basically. So yeah. Right. So this is done. We can go ahead and save it, make sure that all stays. And I just hit save for future, current and future calculations. So again, we have no animations because we didn't save any or set up any animations. What we can do is open up graphics, and we can create some contours or path lines or vectors that can show us what's happening here. So if we double click contour, then we can say, let's look at velocity and do velocity magnitude. But yeah, let's call this velocity magnitude. But we don't really want to look at like, the outer surface of this box is not very interesting. So instead what we want to do is click new surface and then do plane. We can call this I don't know, you'll just call it YZ plane. That's probably the best name for it. And so this will be, the flow direction is Z. So this will cut our trailer in half vertically. And then leave everything else the same, hit create and close. And now we have this YZ plane. So if you select that, it'll put the velocity magnitude contours on the YZ plane. Save and display. So there you go. So now we can see, let me move this over. Yeah, so now we can see this is our 32 meters per second driving velocity. And then we can see actually the boundary layer as it travels over, or as it travels over the sides of our trailer, underneath it, the impinging on the front where it slows down, the drag behind, and the wake. So this kind of shows how there's that slower fluid behind the trailer. But maybe that's like not really what you want. Maybe you'd rather see like some vectors. So you can go to vectors and do the same thing. Velocity, color by velocity and magnitude. And then here, I'll call it the same thing. I think this is a little bit more interesting because we display that. What has happened? Why is it not doing it? Oh, it's because it has the same name. I'll call it a vector. Nice. So now we have all these arrows. And what's cool is that we zoom in here, we can actually see the velocity vectors wrapping around our trailer. Or if you want to move over to this side, we can see the recirculation where the air actually comes back and forms these vortices. This turbulent motion behind our trailer, and the colors indicating the speed. Or what we can do is make these path lines. So maybe I'll name this velocity mag path lines. And let's again do velocity magnitude on that YZ plane. And now we can see these path lines. Bless you. Yeah. You can actually see some wrapping motion there, which is kind of cool. And then if we go on here, you can even better see that circulatory motion on the back end. So yeah, kind of cool. Kind of cool. You can see some of the actual motions in better detail and observe that. I think that's probably all I want to show there. Are there any questions about that visualizing? So I was thinking what we could do unless you have any ideas, I'm open to ideas too, but I was gonna say we could do the same one, but change our turbulence model. So you can see how to look at different turbulence models and you can compare them, that kind of thing. So let's go ahead and save our project. I'm just gonna do that second option there. And then go ahead and close your Fluent. And I'm going to rename this. I'm going to keep the name, but I'm going to add on K omega SST. And so earlier I was mentioning you can duplicate cases, right? So this is a scenario where you want to duplicate what you have. And now I can rename this new version, and let's call it K epsilon actually. We'll do that one first. K epsilon. Go ahead and right click solution and hit edit. And that's all you have to do. The geometry, the mesh is already done. The setup is already done, except for this new thing will change. I guess I should have taken some screenshots of those contours before I closed it, but I can always go back. Maybe what I could do too is I could just share this file with Dr. Vassal, and then you have both examples. So if you want to open them up and look at the contours afterwards, you can, or have a template to go off of. Do that. So, all right. I'm going to set this back to fixed because it changed it because I set it to that adaptive method. Okay, so that looks good. Let's do under models, viscous. Let's do K epsilon this time. And just go ahead and hit OK. And then I guess, so every time that you run a new simulation that you want it to just like run a fresh one, you need to initialize. So go ahead and go to initialization, click initialize. It'll say that there's data files. Do you want to clear them? Yes. So now we've gotten rid of all of our K omega calculations. Then run, and we'll run that one. So what I'm thinking is maybe let this run. Then we can maybe print out contours of velocity and TKE and anything else you want to look at. And then we could do an LES case and then print out TKE and contours of velocity. And then you can kind of observe how the models have different motion behind that, the trailer. Yeah. You see, it's pretty warm. Yeah. That's why I don't run it with more than 4 cores. The GPU is just chilling though. It's fine. That CPU is struggling. Yeah, you could. You could. Yeah. If you have the research license, you can let the GPU help you with your calculations. Yeah. Yeah. Mm-hmm. But honestly, if you're doing anything really heavy on a like in all you have is a laptop, you'd probably want to offload the simulation to like some sort of workstation or HPC cluster for anything real heavy. Yeah. Like Michael's got a whole setup of computers that he runs stuff on, and because laptops they're just not optimized for this kind of stuff. Yeah, for big or powerful cases, it's just not. Yeah, this stuff's easy, but I think most of the stuff that you're actually going to do for like research or something is going to be on a scale that you would want a more powerful, better cooling device.
You have to like share in on size. Like they did a 1 year thing with Chris on the 100-year box, right? There's a scale also as like the time scale.
Not so well, yes and no. It depends on what your cell size is. So, because you could have like a 1 meter by 1 meter, but then have your cell size be a micrometer, and that's going to be way more computationally heavy than having a kilometer by a kilometer, but you have a 10-meter cell size. So it's all dependent on your cells and the physics you're trying to calculate. Could
How we find the equation outside.
yeah, yeah. And there's also like the schemes to having like in CFD, the different schemes, second order, first order, third order schemes. Uh, yeah. And like each one of these models that you can go up here and check energy, radiation, discrete particle tracking. And even for discrete particles, you can have one-way coupling or two-way coupling, where it's like the fluid affects the particles and the particles affect the fluid, that kind of thing. So you can choose. All of that's going to add more equations as have to solve for each iteration, each time step. All right, cool, nice. So save it. And I want to say it should have kept our contours. Yeah, nice. This all stays as well. So we can I think display it. Oh, there it is. Nice. Oh, here it is. Here we go. Yeah, so maybe that's not too obvious. Here's what we can do. If you right click on here and you click save picture, then we can actually just save these as nice PNG format images. Usually a white background is good to have, so you can hit that and save. Here's where it's saving it in this, like I said, the FFF2 directory, but I might go ahead and just save it in my custom directory. So we can call this yeah, let's call this something different. Maybe K epsilon contour. Nice. And then maybe we also do a contour of, oh no. Yeah, put on the YZ plane. Let's look at turbulence too. Look at TKE. We can call this TKE contour. That's a nice little image. So we can do that. And then go ahead and save that picture. Same way. All right. And then, yeah, maybe we do also let's do the vector as well. I think that might be interesting to see. So we could maybe go in here. I think also if you open up the vector menu, you can scale these arrows. Yeah, let's do maybe 3. So if it's hard to see, especially in a region like this, you can go and scale those up. And save picture. And let's do epsilon, velocity mag, vector. Right. And then go and close out of that. Okay, save that. All right, and then let's do one more, duplicate. We'll do this one with LES, and then we can look at the different pictures and let them compare them to each other. All right, perfect. So I'm gonna rename this one LES. And again, open up the solution. Setup and solution both take you to Fluent. And also you can notice that down here it says number of processors. I think you can change this number here to change how many cores you're using, but I forget if you change it in setup or solution. And one of them, if you click it, it won't let you change it. And if you click the other one, it will let you change it. So just good to know if you ever want to run more processors. Yeah, maybe another interesting note is there are lots of CFD softwares out there. Ansys is one of the most widely known and like most industry used. But there are other ones like Star CCM Plus is an industry level software. I think it is an industry level software. And then there's other ones like OpenFOAM. That's a text-based software. So instead of having this sort of graphical thing, it's all done text-based. The one I use is also all text-based, which is good in some senses because you're not having to deal with this GUI. You have more direct control over like what is everything doing numerically. But yeah, there's one called ULAG that's also which stands for Eulerian Lagrangian. That one's also text-based. So yeah, there's lots of them out there, but Ansys is a very popular option. Mm. Yeah, SolidWorks Flow. Yeah. And it's GUI too, I assume, right?
Yeah.
Yeah. So let's do large eddy this time. And then I guess let's go ahead and initialize again and get rid of all of our old results. And then run calculation and calculate. Have you all done large eddy simulations yet in class? No. Okay.
You haven't talked about any sort of model.
Okay. Yeah. So like I guess there's no the turbulence problem's not solved, right? So that's why we have all these models to approximate turbulence. So large eddy is the one that I use in my research, and you're essentially viewing turbulence as a bunch of superimposed rotational vortices. And so large eddy is saying that you're going to resolve your large eddies. Resolve meaning that if your eddy is like, your eddy is like this big, then you have at least 4 grid cells to kind of resolve the motion like this, let's say. So numerically, it can kind of represent that swirling motion because the grid cells can cover that vortice. But then if you had a small vortice like that, that's not resolved, if that makes sense, because it's contained in one grid cell. So the general rule of thumb is that you want your grid to be small enough, say like that size, so that you can resolve eddies this size, eddies that size, eddies this size, and then only have some eddies that are smaller, that are sub-grid scale. So smaller than grid. And you want the number of eddies that are resolved to cover 80% or maybe 90% of your TKE, of your turbulent kinetic energy. So if you can resolve enough eddies that you're resolving more than 80 or 90% of your TKE, then that's seen to be, that's a good grid size, basically, for your large eddy simulation. So the software I use is called UWLCM, and it's specifically a large eddy software. That's all it does. So that's finished up now. So let's go ahead and go down to our save very fast. Then we can go down to our contours and go ahead and save display. All right, let's save that picture. Let's call it, this is TKE I clicked on, so this one. Oh, hang on, did I have this turned around? I guess it did. Oh, hang on. It's plotting static pressure for some reason. Why did it change? I was very confused. Like, why is it turbulent here on the leading edge? Oh, it's because, okay. So I guess I didn't think about this, but TK is not even an option to plot in this case. So maybe I'll just show you this. So here's your subgrid turbulent viscosity. If you want to look at that. Yeah, so maybe this wasn't the best example for me to give you, but you could have done this with K omega and seen the contours between those. And then let's look at vectors. We can at least look at this guy here. It's still set to 3. That's good. Let's go ahead and save this guy. All right, go back to our PowerPoint and let me go here. All right, so let's look at maybe this one. Oops. And this one. Oops. All right. So this top one is the LES, and this bottom one is the K epsilon. So you can see that the velocity is a little bit different. Similar, but it's a little bit different for these. And then I can go and insert the, let's do that one, and that one. All right. So maybe another interesting thing you can look at is if you're interested in boundary layer, then I'll put this in presentation mode. So you can see the boundary layers here, forming there, forming there. Actually, let's do this. I'll just go back into Fluent. That's probably the easiest thing to do. So if we look at our contours again, look at our velocity magnitude contour. It's easiest to see here, but you can actually see the boundary layer forming since this is a wall too. So we have that no slip condition, and then we have the increase in velocity until you get into the free stream flow. So that's really all I wanted to do. Just show you that you can plot those quantities and compare them if you want to. Thank you for your time. I appreciate it.